very good afternoon to all of you. I know it is a very tough time for all of us to stay awake after the heavy lunch. So I will keep it very light and very simple, and together we can help each other to keep awake. Actually, myself and Dr. Naren, we were talking about attending this conference, I think, since the last 3 years. And apparently during this November-December season is a very busy time for me. I usually travel this part of Asia. I think probably for the last 5 years. So I've been in this region during November-December, but we still, this year we were not able to make it, and this year I guess I was lucky to make it to this conference, and I would like to thank Dr. Naren again for this opportunity to be here. And my coordinates you can see on the screen. If those who would like to ask me more questions or more details about something, you can always email me after the conference. Actually, I work for both institutions. I work in a big European project. We are building a big supercomputer in Czech Republic, where we are trying to parallelize huge data or big data, and then we are trying to develop several real-world applications. At the same time, I also lead the efforts of machine intelligence research labs, which we have nearly in 100 countries as of now. So that also keeps me busy with a lot of travel and a lot of projects. And today I'm going to talk to you about something different from what I saw from the papers, from the table of contents from this course reading, which is something new. At the same time, I would like to make it very different from the first keynote speaker who also talked about physical systems. So the last 10 years, I would say, it has really changed our life because of the tremendous growth in the ICT field. The computing itself. 10 years ago, if you want to do some heavy computing, you need to actually buy a cluster or buy some supercomputer which you have to have in-house. But today, even a housewife can afford supercomputing power even from a remote village. So thanks to cloud computing, grid computing, and all other effects. If you look at 10 years before, if you look at commerce, we think about big companies. Boeing, Airbus, GE. But today we talk about something else, Google, Microsoft, Amazon. Anyone can become a seller. If you have an email account, you can actually sell something in Amazon. So before, we used to have a product, we need to have some space to put that, we need to attract customers. So the world has changed in a very big way. And today we are talking about a connected world. When I was a small kid, we used to refer to smartness for kids. We used to call, oh, that's a smart kid, that's a smart guy. But today we don't talk about such things. We talk about smart devices, smart gadgets, smart hospital, smart city. Barcelona, now they call themselves as a smart city. They have smart grid for controlling the power distribution. They have solar powered buildings. They have electric operated cars where you can charge cars after some time. Actually, we have some colleagues from Barcelona where you can ask them how things work there. So the internet has really changed the way we live, the way we interact, the way we talk to each other, even the way we do conferences. Probably without internet, probably Dr. Naren would not have known me, and probably I would not have been able to contact with him so fast and we made this happen. So collaboration has become very easy because of the cyber infrastructure. And here we are talking about cyber physical systems, which are systems, can be anything. And we try to monitor, control using the cyber infrastructure. I will be deviating slightly from the lecture by Professor Mathur because he had a very strong definition of cyber physical systems. But here I am talking about mostly loosely coupled systems. For example, you can have a hospital where you have patients with some sensors attached, and you're trying to monitor them and try to look for anomalies. So it is considered as for me, it is considered as a cyber physical system. I will very shortly show you an illustration of such a hospital. Similarly, in a school, if you want to monitor the school kids, that they're going out of the compound, or they're in the right places at the right time, if you can attach some RFID devices, sensors to each student, you can easily monitor them. And 10 years ago, an RFID device would cost a few dollars. But nowadays, it is only a few cents. If you have 2-3 US cents, you can actually buy an RFID device. So the costs have gone down so low. And these trends are going on a very high scale. You can see devices are being used in many applications, which I will go through very quickly. And the challenge for us is to understand all this complex data surrounding us. So which needs complex solutions, complex methodologies. So in my talk I'm going to focus on those few aspects. So I will quickly introduce what are the main concepts of cyber physical systems with a focus on some applications. I guess some of you may be interested in jumping into some applications and probably you can also contribute something. Then I will try to introduce the concept of intelligent systems. How can you use some intelligent systems for solving these sort of applications, and followed by some examples and conclusions. So I guess all of you will definitely agree that the internet has changed the way we live, mainly because of the rocketing speed of the development of ICT. And it is very difficult for us to even predict what will be tomorrow, because the speed at which things are moving is really very fast. So we can formally define a cyber-physical system as a system which has a tight combination and coordination between computational and physical elements, using the cyber infrastructure. And you can see them already happening in many applications. For example, automotive, in chemical industries, chemical processes, civil infrastructures, for monitoring bridges, for monitoring dams, energy, smart grid, smart prediction methods, healthcare, manufacturing, transportation, entertainment, and even for consumer appliances. So we can say that it is a network of interacting elements with physical input and output, instead of as a standalone device which you will see in our daily life. And recently there are also a few other terminologies, for example, Internet of Things. So here I am also referring to these few technological terms. Internet of Things, Internet of Everything, where we talk about a connected world. It is literally a new concept. I guess the whole concept came into existence probably the last 10 years or so, but it got more materialized during the last 6-7 years. Especially in the US and in Europe, a lot of funding is being devoted to this particular topic because that's the future. So I hope the funding and the research efforts will again help this topic to mature much faster in the coming years. You may have already heard of robotic surgery. A surgeon from US or UK can do a surgery in Colombo. There is nothing special. But imagine the whole thing doing in a virtual environment. If a building is on fire, you want to rescue people inside by sending a group of autonomous robots, firefighters, similarly war fighting. You might have been seeing drones flying all over. Similarly, you can also think about future wars where soldiers won't go into the country or the land. You might send robots, a group of robots carrying all the weaponry and all the devices, and they will fight the war. And you can also use these concepts for augmenting human capabilities. Not as a replacement, but for assisting humans, for improving our lifestyle. We can consider them using in environments. Many times we know that there is a fire only when half of the forest is burnt. Similarly for pollution, when someone collapses, we know that, oh, this is because of pollution. When a river floods, can we predict such things will happen very soon? Similarly, global warming, measuring salt water levels in rivers, especially that is connected to agriculture. Similarly, if you look at cities, you can consider them for monitoring traffic. If you can monitor traffic and if you can simulate that this is going to be a problem, then you can actually redirect traffic so that the situation will be improved. Similarly, pollution monitoring, waste management, it's a big problem for big cities. Similarly, developing intelligent transportation systems, whether we can design systems for the future. E-health is another important area for continuous care, for continuous monitoring of people, or even for sportsmen, for terminally ill patients, or even for surgery. We can see them in retail, for tracking the movement of goods, containers, vehicles, when they leave a plant, when they reach another plant, inventory management, storage management, supply chain management, smart product management. These are all, I would say, some very high-level applications. You can also see things happening in a very low level in daily life. You can just think a bit more by looking into your personal things. If you look at the number of connected devices, in 2003, when we had 6.3 billion population, we only had about 500 million connected devices. It means the population was about 12 times more than the connected devices. This can be mobile phone, can be tablets, can be sensors. But if you look at around 2009, we had more connected devices than people. And the prediction is by 2020, this is going to be about 7 times. So we'll have about 50 billion connected devices. And the population will be only 7.6 billion. So you can imagine we are covered with all these various gadgets, and we need to somehow survive by understanding them and try to manage them. If someone asks me why our life is getting more complicated, I think there is a future. If you look at agriculture, retail, lifestyle, connectivity, social networking, manufacturing, healthcare, tracking people, transportation, you can find applications in almost everything. So you can see there is a massive potential. And the challenge for us is to understand this complex data. If you look just at the social networking layer, where we have all these social networking tools, from Facebook to Twitter to LinkedIn to Google Plus, whatever you name it, for all social networking, plus all the sensors, plus phones, plus various meters. Okay. The figures you are seeing on the screen would be very alarming. For example, about 12 terabytes of Twitter messages every day. Similarly, 30 billion RFID tags are there today. So imagine if they are sending the data every second or every minute, you can imagine the complexity of data. Similarly, phones, sensors, and nowadays you might have also heard people talking about big data. So we also need to advance our technologies and understanding to handle such massive information. The companies, the enterprises have changed during the last 10 years. The data itself has changed. There's a massive volume out there, and the velocity. For example, Twitter messages every second, Facebook messages, the user details, how they are being used, velocity, similarly sensor data streams, variety. Data can be text, data can be numbers, categorical, numerical, videos, images, and veracity. You're not sure whether this data belongs to this particular monitoring system because there are so many overlapping things, or because of say a sensor is faulty. So sometimes you're also not sure whether this data belongs to us. Again, there has been a lot of technologies out there developed by various vendors around the world using various methodologies, infrastructures, applications meant for specific purposes, from business intelligence to predictive analytics and to visualization. You can find a variety of tools. You can also see various tools for handling data, from managing data in a fast way, for example from Hadoop, to data analytics using various methods, from MATLAB to SAS. If you want to go a little bit deep inside knowledge mining, there are also various tools, for example, sentiment analysis, and various other things. But the challenge for us is to convert this data. So many of us, we try to analyze it and then we try to find some information, plot some graphs, show some nice tables, and we think that's it, that's enough for us. But the real importance comes from if we can transform that data to wisdom. And that will really contribute to the development of many things. That requires a lot of coordination between different databases, with different information, different knowledges. You need to interconnect all these things together. Okay? And that is really sometimes not very easy. And that is, I guess, something which we need to strive to develop. So whatever system you're developing, for example, if it is a system to recognize human face, for example, you want to prevent a bad guy from entering the country. So we can see we have this nice cameras in immigration and they take photos. And imagine if the system tells that's a bad guy after 5 minutes, it has no value. Similarly, if you develop a system that can work today but cannot work tomorrow, if you're going to use it in manufacturing, it also has no value. Similarly, if you have a system that can work sometimes with almost 0% error, but it can make a mistake, means it is deadly if you send to space, where we cannot afford to make a mistake. Similarly, understanding complex data, we need advanced methodologies. So a good example is how we park a car in a multi-story garage. We humans, we can easily park a car. If I ask you to park on the 5th story, for a driver, you can easily park it. And if I ask you to park the car within some precision, let us say 5 centimeters from the left side of the parking lot, then an experienced driver would think how I should maneuver at what point. And imagine if I'm going to replace this human driver with a robotic driver. Then you can think about adding all the software programs to make this robotic driver as intelligent you can. And the more software, the more programs you have, then the robot is going to take a lot more time to process and to understand and to make decisions. And the robot is taking 5 minutes to decide how to turn this journey. That's no value again. Then you'll see a long row of cars waiting outside. Imagine it's the automated car park, where the owner leaves the car in the entrance and then he goes away, and then the system automatically takes care of the cars. So we need systems that can also work in real time, which are really useful in practice. And usually, high precision carries a very high cost. And many of the practical problems actually, it can actually tolerate some imprecision and uncertainty. For example, the car, as long as it is in the garage, it should be fine. You don't have to park exactly 5 centimeters from the left side of the parking lot. So the challenge for us is to exploit the tolerance for imprecision and devise computational methods so that we can generate solutions in real time. This, I would say, is the essence of modern intelligent computing. Okay, how to understand complex data, complex environments, and then we can try to develop intelligent methods. And if you look at Mother Nature, you can easily see how Mother Nature solves complex problems. There you can see a group of ants. They are trying to cross a air bridge. You would see how a group of fish or a group of birds, how they try to escape from the predators, or how they move to a new environment, or migrating from one place to another place. When a small baby is born, the baby doesn't have any immunity. Even someone has cold virus passes by, the small baby can catch the virus. But as the baby grows on, the baby not only gets immunity against cold virus, but also against other complex diseases, germs, immune systems. So we can also mimic some of these ideas which we can get from nature for solving some of our complex problems. There has been actually a very interesting research topic along this line, bio-inspired computing, nature-inspired computing, for solving some of our complex problems. And one of the oldest methodology for functional approximation, you have a complex data, and the idea is to approximate a function. Multiple inputs, multiple outputs, and you need to somehow build a model such that you are able to solve a regression problem or some pattern recognition problem, etc., etc. We are trying to mimic a mammalian brain. We can learn from examples, and we are trying to use these concepts for making a machine learn. But for those who are familiar with neural network design, you know that it's not easy to design a network. Very often we are challenged by questions like, what is the optimal number of neurons? How many hidden layers I should use? What learning algorithm I should use? What parameters I should use? How long I should train? When should I stop? And apparently there are no well-defined answers. So basically we are trying to solve the NP hard problem. So for a fixed network size, and for a given application or for a given data set, finding optimal values of this weight is proven to be an NP hard problem. So we use several learning methods. In literature you might see hundreds of learning methods. And they would say that this algorithm is the best, this is the best, but we have the no-fluence theorem which says that there is no single optimization method that can solve all categories of problems. Some learning method would work well for some class of problems, but if you take the same learning method for another class, it might not work. So we are actually verifying the no-fluence theorem when we are trying to use neural networks for different applications. So how can we get over that? Similarly, if you look at fuzzy logic, it's a very good tool for approximate reasoning. I'm sure all of you are users of fuzzy logic, even though you might not be familiar. If you have a modern camera, or if you are using a rice cooker, this is a complex rice cooker. It's a neurofuzzy rice cooker. Basically, if you just put the rice inside, it will set its own cooking time. It can learn from experience, etc., etc. So fuzzy logic provides a very nice framework to model imprecision and vagueness. For example, if I tell you John is tall, I'm sure all of you understand how tall John is. And if I ask each of you, you will say, for John can be 160, 170, 180. And each of us have this very nice definition of height, which we learn from experience since we are a kid, through our parents, through our friends, in our school, in our university. We try to fine-tune that definition somehow. And all of us have a different way of defining it. If I say that I was the tallest when I was in I was the shortest when I was in Norway, you can imagine. And if I go to Japan, probably I'm okay, I'm doing okay, I'm sort of average or better than average. So how can we make a machine understand such things? If I want to program a machine telling that, turn on the air conditioner if the room is warm, and what does warm means? Again, warm means different to different people. Someone is from Africa, probably for him 30 degrees is nothing. or even 35 is nothing. But if somebody is from Norway, probably it will be like Owen. So how can you make a machine understand such things? Fuzzy logic provides a very interesting framework to model this type of imprecise and vague expressions, or that comes from data. There are also several fuzzy inference methods using if-then rules. You can actually build complex systems for various purposes, for functional approximation, for understanding some data. But again, for those who work on fuzzy logic, I'm not really sure how many of you work on fuzzy logic, fuzzy inference method, fuzzy systems. It's again not very easy to get something to work. We need to decide the input-output variables, fuzzy inference system, which method I should use. There are also a few other methods, I just shown you two, but there are also a few others. You need to decide the type of ambitious functions, you need to build a knowledge base, you need to tune the ambitious functions, the parameters. Okay. So it is again a complex challenge to get it to work. Okay. So I will try to show you some of the methods which we are using, or which we have developed during the past few years. Another tool for solving optimization is the class of evolutionary algorithms based on Darwin's theory of natural selection. Fitter the parents are, they will find the opportunity to get food and produce offsprings. And the basic idea is offsprings are always better than the parents. So mathematically we can define something like that: x t plus 1 equals x v x t. So xt is the current population, which is operated by a variable operator, and then you select using a selection operator, and then you get the next population, x t plus 1. We started the population of solutions, we select the best out of that, we alter them or reproduce to the next generation. We keep on doing this until we get the required solution. One of the most successful algorithms in the field of computation intelligence. Annually about 5,000 papers are published using this very simple concept, because I would say one of the reasons is because of its immense success in many practical applications. It can be used very much when you don't have enough information about a search space, and we have population of solutions. We end up with a population of different solutions the user can pick. But again, getting an evolution algorithm to get into real work is not sometimes very easy, especially if the search space is very complicated. We need to tune the parameters such that we trade off the search or have a balance between exploration and exploitation.